The session, fifth day, second session starts with Dr. D. Ruben Sudhagar. He is going to talk about battery storage system, lithium ion, flow battery, and the sodium ion. Welcome, sir, Dr. Ruben Sudhagar, sir.
Hello, sir. Good evening.
Good evening, sir. Fine, sir. Very fine, sir. Shall we start, sir?
Sure. Certainly.
Please. Dear participants, once again, sir, once again, welcome you, sir, for this wonderful session. I call upon Mr. Kaliraj to give a small introduction about yourself, about today's speaker.
Okay, sir. Behalf of management, principal, coordinator, and co-coordinator, head of the department and faculty of St. Peter's College of Engineering and Technology. Thank you, sir, for accepting our invitation to deliver the guest lecture on 6 days AICTE-sponsored Adal FTP on energy conservation and storage devices for global sustainable development goals. Brief introduction about today's session speaker, Dr. D. Ruben Sudhagar, sir. Dr. D. Ruben Sudhagar is Associate Professor in the Department of Energy and Environment, National Institute of Technology, Tiruchirappalli, short NIT Trichy. Prior to joining NIT Trichy, he was serving as Assistant Professor in the Department of Chemical Engineering, National Institute of Technology, Suratgal, Karnataka. Before starting his experience in the academic, he was a lead research engineer at the Renewable Energy Innovation Center of Siemens Technology and Service Private Limited, Bangalore, working on various energy conservation technologies for decentralized power generation. He earned his PhD from IIT Madras and MTech on Energy Conservation and Management from School of Energy, Tiruchirappalli. His research interests include energy storage systems, battery thermal management, thermochemical conversion of coal and biomass, energy system analysis, CO2 capture technologies, and energy conservation and management in process industries. He has published his research findings in several reputed journals and conference proceedings. As a qualified energy auditor and manager, he offers consultancy service to industries on energy conservation and management. Once again, I am welcoming sir for this 6-day Adal FTP on energy conservation and storage devices. Kindly request to deliver the guest lecture on battery storage devices, lithium ion, flow battery, and sodium ion. Over to you, sir.
Okay. Thank you very much for a kind introduction, sir. It's wonderful to hear. And a very good evening to the organizers and the participants. At the outset, before I start, let me thank the organizing team and in particular Professor CHINNAPANDIAN for the opportunity. In US, there used to be probably early 2000s, there used to be something called as a food versus fuel crisis. I don't know how many of you have heard about it. Okay, corn was infamously diverted for the production of ethanol largely, and then the food prices, especially the corn prices, went up. There was large-scale agitation, and then they came down in the diversion of the corn for ethanol production. Similarly, here is a food versus fuel crisis. There's a food before you, different as I originally agreed for, but however, I am there in the area that, so it's going to be the lithium ion and vanadium flow batteries that I'm going to talk about. And then I'll also talk about the R&D that we are doing. Means when I say we, I and my students are doing at NIT Trichy, the Department of Energy and Environment. So I will navigate through the presentation on these heads. I will talk to you about why is it important to talk about the energy storage and how do batteries as energy storage systems are relevant in the current energy scenario. And I'll take you through the basics of lithium ion batteries in terms of how does it function, what are their advantages and limitations compared to the other batteries, especially the lead acid batteries that we had been using long since. And I'll talk about the R&D on lithium-ion batteries and move on to talk about the basics of vanadium redox flow batteries and then R&D on FBRFBs at NIT Trichy, and then close the session by some final remarks. My research, if you look at, is largely towards the engineering aspect of batteries. And so if there are chemists who are expecting on electrochemistry, I'm sorry, I'll not be talking much about electrochemical research aspects of this battery. Let me put that at the outset. I hope it's good to go. Let's start with a bit of a background on why is it important to talk about energy storage in the current scenario. In COP26 meeting, we, India, have given a great promise to the global nations that we will achieve 500 gigawatts of renewable energy target by 2030, and we will have 50% of the energy coming from renewables by certain period, and then we will reach net zero by 2070, and so on. And this is a very ambitious target in my view, with about 58% of the today's primary energy consumption of the country coming from coal, and about close to 48% of the electricity installed capacity in our country is contributed by coal. This is certainly an ambitious target that we have set. However, moving to renewables is certainly happening. We are transitioning in terms of energy very sharply, moving towards the renewable energy target that we have set. For example, if you look at solar penetration, we have seen little over 20% already through the National Solar Mission. And if you look at wind, we have considerably penetrated into the renewable energy market. These are good signs, and we are already seeing close to about 47% of the total electricity coming from the renewables. So 50% from renewables or non-fossil fuels, including the nuclear power, is not going to be that difficult. But what is the problem with these renewables is that it is intermittent, right? I call this sun as an office goer. It comes at about 6:30, 7 o'clock, and then leaves the office by 5:30, 6 in the evening. And we cannot stop sun, or we cannot ask sun to come earlier. And if you look at wind, it's like work from home culture. Okay, whenever it blows, we will have to use it. That's all. It's very difficult for us to control the wind. When I say control the wind, ask for it at certain velocities and so on. So this being intermittent and not so very constantly available all the time in the intensities that we require, as we have planned to have our energy demand satisfied, that's going to be difficult to rely on these kind of resources. And here, the energy storage systems are going to be a big enabler in this current scenario of moving towards more of renewable energy contribution to our energy mix of the country. Okay, so that's how the energy storage systems becomes more relevant in the current scenario of the great energy transition that we are going through, or we are ambitiously aiming at. Okay, so here is an AI generated picture, and you see a lot of things. You see wind turbines, you see solar, you also see grid lines, grid stability. Energy storage systems favor grid stability. You see electric vehicle, they're being charged by the electric charging facility. We have homes being powered by renewable energy sources, and so on. So this kind of tells you how important is the energy storage system today in the current scenario of energy mix that our country has, as we move towards the ambitious target that we have set. I hope my slides are navigating through. You're able to see the relevance of battery energy storage now?
Yes, sir.
Thank you very much. Okay, good. So while that says about the importance of energy storage system being a big enabler to have much of renewable energy penetration into the market, and to produce more of a cleaner energy, reducing the coal contribution to the primary energy mix. Now we are moving to talk about battery energy storage in specific. This type of energy storage, the electrical energy storage, is not something very new to us. We have been living with batteries for a very long time. But unfortunately, we were only having what are called as non-rechargeable ones for a long time, like the lead acid batteries. Now the world has moved towards rechargeable batteries, thanks to lithium-ion batteries, which are largely being researched and commercially available as a rechargeable battery today, which is one of the systems that we will be talking about today. So why is it the battery energy storage systems are becoming important today? What are the drivers is what this particular slide is talking about. We see that the electric car sales have gone up, and it has exceeded 14 million units of car sold globally in 2023. That is something like 35% higher than the 2022 sale. Okay, it means we would be requiring more of EV charging stations, and there is no fun in having an electric charging station with electricity fueled by coal. That's only shifting the pollution from the roads to a particular centralized power generation systems which use coal. That's not going to be really benefiting us in real sense. Okay, so the electric cars are penetrating. We have had FAME 1, FAME 2 schemes, and then we had EMPS schemes till about September 2024, I guess. So, and I would certainly expect some more schemes to come to promote electric vehicles penetration, or making us making more of us to buy electric vehicles in the future. Government is working on it. And in such other emerging economies like China, we see that the electric vehicles represent 50% of the new car sales. So there is a lot of EV that's going to be on the road, and we are going to have a lot of demand on the EV charging stations, which must necessarily be fueled by renewable energy source, electricity produced from renewable energy source, and that requires energy storage system like battery, certainly. I did talk about energy transition, and the global investments has already reached $2.1 trillion. And that means it's a great sign that every nation is trying to move away from coal or any of the fossil resource. Again, the relevance of BESS is only increasing because of the energy transition. If a country is sluggish in this energy transition, it's only going to cost the country more. Okay, and so BESS will help us have a lower energy transition cost for the country if we have an affordable BESS because of a good research and development done by the industry and academic institutions. Like the global battery market is about 134.6 billion in 2024. It means we are already producing a lot of batteries, and if you look at the compound annual growth rate, it's close to about 16.5% expected to be when we move from 2025 to 2030. Okay, and the manufacturing capacity is going to exceed 9 terawatt hours by 2030. So all this tell us that we are going to have a big ride on the battery energy storage system. And so it becomes very important that we spend some time or we industries and the academic institutes work on BESS and make it more affordable and safer is what is much implied by this particular. Good, I'm going to talk about two important types of batteries today. One is a very good performer, very strong performer among the batteries that we have as options, which is the lithium-ion battery. When I say very strong performer, I'm talking about its high energy density and so on. The other guy is going to help us in terms of increasing the scale of the batteries and in terms of operating very safely. So let me first take up the lithium-ion batteries and tell you all that why is it lithium-ion batteries are a strong candidate among the batteries today, which is inevitable when we talk about rechargeable batteries. They are lightweight and of compact in design. There is no other batteries parallel their efficiency, certainly not the lead acid batteries, especially for the portable applications that we are largely using it now. And if you look at the lifespan, we are talking about 8 to 10 years. That's equivalent to about 2000 charge-discharge cycles. Okay, the lead acid batteries, you have been using it in very many applications. That's not giving us a very good lifespan. So that way, lithium-ion batteries are also very good among the batteries. The most important strength of the lithium-ion battery is its energy density. We are talking about something like 200 to 300 watt hours per kg. And this battery has a potential to reach 1250 watt hours per kg. That's phenomenally high energy density compared to what we are talking about as other batteries. If I should make a comparison with the redox flow battery that I'm going to subsequently talk about, which is the vanadium redox flow battery, that has only 1/10 of the energy density of lithium-ion batteries. That tells you how powerful is the lithium-ion battery in terms of the energy density. The second thing is about low self-discharge. We are talking about something like less than 1% of charge being lost per month. Okay, yes, of course, the first 24 hours of the full charge, it loses a bit more. But if you talk about a prolonged period of a month or so, it's less than 1% of charge lost. And so that's a very good self-discharge that the lithium-ion batteries exhibit. It means the capacity lost is lower even if you keep the batteries inactive for a while. Quite often we talk about energy memory effects of the batteries. For example, if you talk about nickel cadmium batteries, that's a big weakness of those batteries. But lithium ion has a very non-significant energy memory effects. I hope you understand what is the memory effect. For those who are not aware of this memory effect, what do I mean by memory effect is like, let's say you have a particular charging discharging pattern. Let's say you have charged the cells which are there in your laptops when it shows 50% of the power still left over. Okay, the batteries have the ability of remembering your frequent charging discharging pattern, and then it starts following that, and that leads to the short discharging cycles, short discharging spans, and so on, which is not desired. So such things are not there as far as the lithium ion batteries are concerned. Safety, I'll come to the real problem of safety with lithium ion batteries. But however, today's lithium ion batteries that are commercially available are made with safety standards, international safety standards, either the IL or the IEC that you talk about, which are resistant to water. Explosions, I'll have to qualify them, and I'll come to that little later. And you see them, lot of them being used in transportation vehicles and electronic devices. Okay, faster charging times, certainly it has a reasonably good charging time. You don't have to wait too long for charging lithium ion batteries when compared to the lead acid batteries. So that's about the positives of the lithium ion batteries. And if you look at how the basic lithium ion batteries work, you have an anode as given in the picture onto the left side, and you have cathode on the right, and you have a separator in between, okay, that keeps certain things from moving from one side of the battery towards the other. And you have the electrolyte, which is generally an hydrocarbon liquid, which you quite often see in most of the lithium ion batteries. Apart from this, you have current collectors, one on the anode side and the other on the cathode side. So the lithium ions move from the anode to cathode and cathode to anode, which is what is this separator permeable to. And it does not permeate the electrons to flow through these separators. Electrons flow through the external circuit via the load that you're talking about whenever the lithium ion moves from anode to cathode and cathode to anode during the discharging and charging cycles respectively. The biggest problem with the lithium ion cell that we face today, that you also read as news in newspapers and what you watch in media, is that this separator giving away. Sometimes when the separator gives away, there's a mix of these elements on either side of the separator gets mixed up, and that's a very deadly situation wherein the short circuiting of the battery happens, which leads to an explosion. That's one of the important risks that certainly we certainly have with the lithium ion cells today. And one of the objectives of our research is to see to that the temperature levels are not rise to that levels where the separators can give away, is what we are working on, and I'll talk about that little more in the slides to come. There are different types of lithium ion cells, as you see over here. There are prismatic cells, there are pouch type cells, and there are button type cells. Button type cells largely being used in portable applications, like for example your trimmer, your pacemaker, and other such small devices. And pouch cells are also used in portable applications. Prismatic cells are used in mobile phones and so on. Cylindrical cells are used in laptops. For example, if you open the laptop battery, and you will be able to see cylindrical array of cylindrical lithium ion cells today that are largely being used in laptops and such other devices. So you have several options in terms of the shapes, but however, fundamentally, these types of cells are very similar. Only the shape is different. Fundamentally, they are the same. When you talk about slightly large applications, like for example, you're talking about EV, okay? EVs require, and let's say we are using cylindrical lithium ion cells, we need large number of them to be used to run the EVs. So from a single cell, you make what is called as a module, okay? And these modules are basically collection of cells configured in a certain fashion, connecting them in a series or parallel, depending on what voltage and what current you are desiring to withdraw from these modules. And these modules are the important units, and this is where a lot of research is going on. Okay, and several such modules form what is called as a pack. If you look at periods late 90s and early 2000s, if some cells in this pack go wrong, then they have to change the whole pack. But nowadays it's not so. We have systems to identify which of these cells have gone wrong and can only replace that and then configure it in such a way to make it rework again, put it back in the application and then make it work again. So that also benefits or that also favors lithium ion cells among the other cells for its better use in different applications. So these are the applications that you can see in the market. And you see there are a lot of growing markets, especially in terms of the EVs, heavy duty cars, trains, aviation industry, grid level energy storage systems. Okay, grid level energy storage systems also require thing, but we are not there in a very comfortable scenario satisfying the grid ESS now. There are other candidates like the vanadium flow batteries that can very well overrun these lithium ion batteries in terms of the capability satisfying very large capacities like the ones that are required for grid ESS. Then on the other side, you see portable electronic devices, smartphones, laptops, medical devices, personal care devices, and power tools. We have a very good market already there. In fact, it's saturated. So a lot of development is going to happen on the other side, onto the left-hand side of the diagram, the transportation, energy storage systems for large power requirements. Okay, so that's where the future of the lithium ion applications are going to be, if you look at. Good. With that, basics on the lithium ion batteries. I'll talk about a bit on what kind of research we are doing at Department of Energy and Environment with respect to lithium ion batteries. So let me talk about the biggest problem with the lithium ion batteries, because the research that we are doing is very much connected to this. One of the important objectives is to somehow avoid these kind of problems that avoid happenings, avoid such problems in lithium ion cell. So if you see the lithium ion batteries, they are very sensitive to the temperature. Its performance is sensitive to temperature. More importantly, its safety is very sensitive to the temperature. Means you can get a better lifespan for the battery and a safe operation if you are operating the lithium ion batteries in the range of 15 to 40 degrees Celsius. Anything lower and anything higher is going to be a problem. So you must somehow do something to keep these batteries, modules, battery packs within the temperature range of 15 to 40 degrees centigrade. Let's say if you do not do a good job in keeping these temperatures, the cells at these temperatures, there's a possibility that a condition called thermal runaway can happen. So basically, there's a heat generation, uncontrolled heat generation, which will lead to temperature rise. And this temperature rise would lead to higher reaction rates. And the higher reaction rates will only liberate more heat, and that would go on in cycles and lead to explosion. Okay, and let me give you some numbers so that we can understand the time scales at which these things happen. If there is a thermal runaway, and if a separator gives away, or if there's a thermal runaway, then you will see that less than 5 seconds, you will see that the single cell will start catching up fire. Okay, and in next 5 to 20 seconds, about 6 to 8 cells will catch up fire. And in next 40 seconds, the whole module, about let's say 18 cells or 20 cells that you have, will start catching up fire, and it will explode very ferociously, and that is going to be very, very dangerous a situation. So here is a video that I would like to play to show you how the flame propagation after the thermal runaway as initiated is what you can see from this. So basically, you saw spurts of flames coming out from the lithium-ion batteries, isn't it not? So the basic reason for this kind of explosion is that the electrolyte that we have been talking about is basically an hydrocarbon fluid, and when the temperature of the battery increases, these hydrocarbon liquid starts turning into vapors, and these vapors are highly inflammable. Okay, so given the temperature being high and these hydrocarbon vapors emanating from these batteries is a perfect situation for a very big fire, right? Like the ones that you saw. That's the reason why the lithium-ion batteries are considered to be unsafe in that way if you don't operate them in the within the temperature range or the limit that I was talking to you about, which is 15 to 40 degree Celsius. So towards minimizing this effect, 1 minute, let me. So towards minimizing the chances for this to happen, there are a lot of cooling systems that are being tried out in the research arena. One is the air cooling. The simplest of the possibilities that we can think of is that we use air to cool either the natural convection using the natural convection phenomenon or forced convection phenomenon, right? It's quite simple when compared to the other techniques of cooling. But however, the question is, does that cool the cells to the required temperature range that we desire? Is a very important question. That also depends on at what rate you are withdrawing the current from the batteries during the discharge of the batteries. If you look at Toyota Prius, Nissan Leaf, Volkswagen, and so on, they tried air cooling mechanisms. But however, if you talk about Nissan Leaf, for example, that went through a lot of problems as far as the thermal management of the batteries is concerned. So I would certainly consider air cooling is not going to satisfy given the power ratings being highly demanding because of the electrical demand increasing, leading to because of the sophistication that we are having in the applications that we are using today, be it a car or be it any portable devices. We have a lot of additional features which would demand for more electricity and so on. So air cooling is very limited in its ability. Then people tried out what is called as the fin cooling, okay, increasing the heat transfer surface area so that you can have a better cooling is what. But the problem with that is you are going on adding weight to that. Okay, so weight is a very sensitive factor, especially when we are talking about electric vehicles kind of a scenario. That's not going to be very helpful. It's only going to add to the burden of the batteries. It has to pull through that weight. So the weight outweighs the benefits that we get by increasing the surface area for the heat transfer. So this is also limited. Then people started using what are called as phase change materials. Okay, this was reasonably good in terms of removing the heat, but the problem is the volume of the systems started becoming high. So volume is also important. We want this vehicle to be very conservative in its volume, very light in weight, and so on. So there's a problem with the volume desirability on the less volume if you use phase change materials. So the material cannot transfer heat. Okay, it can pick up heat from the batteries, but then it has where should it will just have it in them. There is no other medium that's picking up heat. Only the airflow, quiescent airflow around it gets some heat from the PCM. So that is also another limitation of the PCM. And the heat removing ability was also restricted in the initial days. Now there are a lot of PCMs being tried with very good heat removal abilities. I'm going to talk about one such experiments that we have also carried out. Then there's something called as an indirect contact liquid cooling. This certainly is better in terms of the efficiency, in terms of cooling. But you require coolants without corrosion, that may not lead to corrosion. If that is going to lead to corrosion, then you must have something called as a corrosion inhibitors and so on. Yes, many electric vehicles like the Ford, Jaguar, Tesla, BMW, they use this kind of cooling techniques. Now people are moving towards what are called as direct cooling, direct liquid cooling techniques, or what are called as immersion cooling techniques, because the amount of heat that can be removed from these batteries are going to be very high with this kind of direct contact liquid cooling. As of today, as far as my knowledge goes, there are no, sorry. Okay, so direct contact liquid cooling is what is being tried out because it is very efficient compared to the all other cooling methods that we have been talking about minutes before. So there are no commercial vehicles that have started using direct contact liquid cooling method yet. And so a lot of research is going on, and a lot of improvements are being done in direct contact liquid cooling. In this case, you will have the whole module submerged into the liquid, which would remove heat. But the problem is that it would require for more specialist fluids. When I say specialist fluids, nothing conducting can be useful, right? As you very well guessed it. The fluids must be dielectric in nature. They shouldn't be electrically conducting, but it should be a very good thermal conductor, right? So especially when you talk about race cars, when you're talking about high performance supercars, then this cooling technique will certainly be needed. Okay, and that is if that is going to be certainly demanded. I mean to say the other methods of cooling is not going to greatly help us in such high performance supercars. So already 3M, a company you must be knowing about, is trying out a liquid called Novec 7100 engineered fluid, but it's a very expensive fluid. We're talking about a liter costing about 8,000 or 10,000 rupees or something like that. Okay, so that's very expensive. So we are looking for very cheap liquids that can act as direct cooling medium for lithium-ion batteries. And the research that we are doing here is towards achieving this objective. So as I told you, there are no commercialized vehicles still operating with this direct cooling type systems yet for cooling the batteries. This would certainly improve the heat transfer much higher than the other methods that we have been talking about. It would improve the pack temperature. More importantly, it will keep the pack temperature uniformly. Okay. See, two important parameters you look at when you are monitoring the batteries when you are thermally managing it. One is the surface temperature of the battery. What is the maximum temperature of the surface that these batteries are achieving, the cell surface is experiencing. Second thing, what is the maximum temperature difference across the module? Any two locations, the minimum and maximum. The difference between these two is also an important parameter that we must talk about. While I told you the number for the maximum temperature that we should not exceed 40 degrees centigrade, on the lower side we should not go below 15 degrees centigrade, there is also a norm that we should generally, a norm that is generally desired in the industry is that the maximum temperature difference within the module should not exceed 5 degrees centigrade. Okay, so the del T within the module should not exceed 5 degrees centigrade. So uniformity, temperature uniformity is also a important parameter that we would be monitoring when we are thermally managing these batteries. Okay, so basically this is to protect the cell-to-cell thermal runaway. In between the cells there will be gap. The fluid that we are passing in will flow through the interstitial spaces between these batteries, and so that's going to avoid or protect the batteries propagation of the flame. As you saw in the video that I showed you, there was some propagation of the flame when one cell started firing, the nearby cell also started getting into fire, right? So this can be probably protected, this can be avoided, or this can be slowed down. The propagation can be slowed down by having these kind of direct liquid cooling systems. So this would also lead to higher charge and discharge rates. So you can quickly charge, and you will be able to cater to the high power requirements, like in the case of the high performance supercars. So that this would enable, the direct liquid cooling can enable us that features very, very favorably. And it would also increase the battery life. Now we talked about 8 to 10 years. We are aiming at 15 years of battery life by improving this cooling technique, or by using the direct cooling techniques, which is currently only 8 to 10 years by the other methods of cooling. So immersion cooling is slowly being tried out, and we are looking to see something commercially happening by 2026. And by 2031, we would see a lot of commercial applications using dielectric fluids for liquid cooling, direct liquid cooling system, indirect cooling liquid system. This is from the projections that are there in the literature. Given the source, you can go and look at them to know more about these projections and what are the assumptions behind these numbers. So certainly direct cooling system, liquid-based direct cooling system is going to be seen commercially in the near future. And so the research that I'm going to share with you, what we have done here, is about direct liquid cooling. So we used lithium-ion batteries of 18650. This is called as the form factor. When I say 18650 cell, it means the diameter of the cell is 18 mm, and the length of the cell is 64 mm, and 0 indicates it's cylindrical in shape. So now we are also working on 21700 cell. So these are the two cells that is also used in electric vehicles. Largely 18650 is used, and 21700 is being tried out in certain vehicles. So you see the module that has been fabricated by connecting them in certain fashion. When I say certain fashion, in the present context, we have 5 series 4 parallel, 5s4p configuration is what we have done. We have used 20 cells. Okay, and the spacing between the cell that we have maintained is 2 mm. The nominal capacity is 10 amp hours with nominal voltage of 18.5 volts, and the power capacity of 185 watt hours. And the maximum amount of maximum discharge current that you can expect is 14 volts. Sorry, a discharge voltage, the discharge current is 30 amps, and we have used nickel strips to connect these cells in series and parallel. And the strip thickness is about 0.13 mm, and we have used resistance spot welding to connect these cells, as you see the machine over there. And I must say this: we do have this facility in a certain capacity here in our own laboratory at the Department of Energy and Environment. But we work together with an industry called High Energy Batteries India Limited, which is there in Trichy. And this particular machine that you are looking at here in the picture is the one that's present in high energy batteries. Okay, And we have thermocouple connections. We have soldered them to each of those cells, individual cells, so that we could monitor the cell surface temperature with respect to time. We have done different kinds of experiments. We tried out the natural convection cooling, so that we'll be able to report how far the direct liquid immersion cooling is superior compared to the natural convection cooling. That's also followed in certain vehicles or certain applications. This is the experimental setup. Here is a battery tester which helps us charge and discharge at a certain C rating. And we have the module kept inside the acrylic casing, and we have BMS, which is called as the battery management system. The very important function of the BMS is to see to that the discharge and the charging happens uniformly across the cells in the module. If you do not have BMS in place, you will see some cells with high amount of energy in them, and some cells have already discharged to a large extent. So this kind of non-uniformity will lead to problems and will also lead to safety issues, not just the performance issues, but also the safety issues. So BMS is a very important component that is to be there to regulate the flow of current from each of the individual cells, so that you see all the batteries SOCs are at close to uniform state of condition. Okay, and we have connected, as I told, we have connected the T-type thermocouples to individual cell surfaces, and that they are connected with the data acquisition system that you see onto the right side of the setup. Okay, and we have performed at different C rates: 0.5, 1, 1.5, 2, and 2.5. Maximum we have gone up to 3 C rating. That's good enough because much of the electric vehicles that we see here in India uses a C rating well within the 3 C rating. So these studies can directly be useful for the electric vehicle applications or wherever the C ratings that are. To talk about the immersion cooling setup that we have used. So we have used the same kind of setup, except that we have a peristaltic pump over here. So the peristaltic pump helps us maintain a flow of the coolant, which is the liquid that we have tried out, to flow in and flow out of this enclosure within which the lithium-ion battery modules are positioned. Okay, so we can vary the flow rate, and that is we have done studies at different flow rates and so on. This is a setup where you see the phase change material is used for cooling. So you see the white stuff inside the acrylic enclosure. That's the phase change material. That's the whole cell setup is the module is immersed in the phase change material over there. That's the only difference compared to the other setup, what we saw for the natural convection setup. The only difference is the PCM inside. So these are the thermocouple positions. This would be useful if you want to relate to the cell temperatures, individual cell temperatures, with the plot that I'm going to show you in the later part of the slide. Okay, so from one side of the module, we will be letting the immersion cooling fluid flow, and from the other side of the module, it will exit. So here you see that we have used two liquids. One is called as the terminal oil. The other one is called as the mineral oil. I'm not going to talk about the properties of this. This is all there in the open literature. If you would like to look at, kindly look at them. And this is compared with the temperature variation with time of the surface of the individual cells. So each of those lines that you see correspond to the individual cell surface temperature. And this is all at 3 C ratings. I've taken this, I've only given it for the highest C ratings. I've not given it for the lower C ratings over there. 1, 2, 3, 4, as I told you earlier, relates to the thermocouple positions that I showed you in the last slide. Okay, so you see that the cell temperatures are widely varying between each other, right? So the cell that is sitting at the center of the module is going to experience a higher temperature compared to the cells that are sitting at the periphery. Okay, that is why you see the wide variation in the cell temperatures, somewhere from about 27 degrees to about 37 degrees or 36 degrees. A 10-degree difference problematic if you want to have a better performance and better safety conditions to be maintained. If you look at the natural cooling, you see the highest temperature that a cell faces in the module reaches to close to about 81 degrees Celsius. Okay, that's very high temperature when compared to the desired temperature limit that we wanted to maintain, which is somewhere between 15 to 40 degrees Celsius. Okay, so certainly natural convection is not helping us. So we move on to talk about do some forced air cooling. It has considerably come down. The sun surface temperatures considerably come down when compared to the natural cooling. We are seeing close to about 49 degrees Celsius is the highest temperature in the module, which is very good, but not sufficient yet. So then we move on to the use of the liquid immersion cooling. We have come down to close to about 42 degrees centigrade with respect to terminal, and with respect to the mineral oil, we were able to reach about 40 degrees centigrade at 3C rating, which is the highest C ratings that we had. This is about the maximum cell surface temperatures at different C rates, and the solid lines show the experimental values, and the which are dotted is about the data from the simulation studies. So we also did some simulation studies using ANSYS, and then we were able to predict the temperature rise of the battery surface with respect to time. And surprisingly, the deviation from the experimental results were very, very low, showing that the simulation was able to capture the temperature rise of the batteries. So this will help us go further and investigate the lithium-ion batteries for higher C rates of let's say 8, 10, and so on, which is very much demanded in high performance cars or race cars and so on. That would be the thing. We don't have to do experiments, which is going to be relatively unsafe in a way if something happens. So we can rely on these models that we have built to predict the temperature of the lithium-ion batteries at higher C rates. This is about the terminal oil, and the earlier one was for the forced cooling. And here also you see that the model is capable of predicting the cell temperatures well. And so immersion cooling studies can be done for higher C rates using this model. We'll have to simulate to higher C rate conditions, and that will be able to understand what happens to the temperature rise of the cells in race cars and so on. This is the maximum cell surface temperature for the mineral oil. Although we are not able to predict well in certain conditions, for many of these conditions, many of the C rates, we are able to achieve good predictions using the model that we have with respect to the mineral oil too. Here is a summary, a very consolidated picture, a comprehensive picture of the results of what we have studied. You see that the maximum temperature, as far as the maximum temperature of the cell surface is concerned, the natural cooling method is not helping us to keep the temperatures within the desired limit. Okay, so we cannot use natural cooling. It's inadequate to use natural cooling for 18650 batteries, what we have studied in. If you look at forced air cooling, yes, till about 1.5 C discharge, we are able to see to that it takes care of the cooling well within the temperature limits. But if you look at beyond 1.5 C rates, 2 C rates, they are moving above the desired limits. If you look at the immersion cooling using terminal oil and the mineral oil, we are able to push it to 2C discharge levels. We are able to satisfy the cooling requirements till the 2C discharge rates. They are doing well. However, PCMs, pure PCMs, are not able to do the job currently when compared to the immersion cooling using liquids like terminal oil and mineral oil. So that's the important inference that we came up with from our studies. And we also measured the maximum temperature difference. A very similar scenario prevails, stating that the natural cooling is not satisfying. It is going beyond the 5-degree temperature difference, which is acceptable or tolerable. And the immersion cooling using terminal oil and mineral oil are able to do the job till about 1.5 C discharge, while the PCM is able to do is able to maintain a uniformity till about 2 C discharge conditions, well within the 5 degrees centigrade, which is the desired temperature difference in the lithium-ion batteries. This is again to show you about the natural cooling experiments using PCMs, okay, and SSPCM. So the pure PCM was not really doing a great job. So what we thought was, how could we improve the PCM to have a better heat removal from the batteries, is what we were looking at. So we modified the PCMs in certain ways. One, we synthesized what are called as shape stable PCMs, which are high performance PCMs compared to pure PCMs at affordable cost. The other option we had was to encapsulate the PCMs, but encapsulation is a slightly expensive technique or expensive proposition when compared to what is called as the shape stable PCM synthesis. So we were able to produce shape stable PCMs, composite PCMs, using two materials. One is called as the expanded graphite, and the other one is biochar. The idea is to improve on the thermal conductivity of the PCM so that the rate at which the heat is removed from the lithium-ion batteries was improved. Okay, so we were able to see that the SSC PCMs, which are basically shape stable composite PCMs, did a better job compared to the PCMs, as you see over here, in terms of maintaining a uniform temperature and also bringing down the cell surface temperature close to the desired values of. Here is the maximum temperature history for different cooling methods. I would only like to talk about the higher C rate, which is the 3C rate, considering the interest of time. If you look at the natural convection air cooling, look at it, it's very, very high above the PCM. And you see the SSPCM assisted cooling is better compared to the PCM assisted cooling. The red line is the PCM assisted cooling, and the blue line is with the triangular marker points is the SSCPCM. Okay, we were able to publish these results in the Journal of Energy Storage with my student. Muthaiya Gaud was my PhD student who did these studies. I should acknowledge his efforts. Again, here are the comparison of the SSC PCMs with the PCMs. Certainly, in certain discharge rates of 1.5 discharge rates, it's doing a better job. We are able to see that the battery temperature comes down with the SSPCM. We also use what are called as the ANFIS modeling to predict the temperature of the surface. See, one is getting to do the predictions using mathematical modeling. The other one is to use a black box kind of modeling using ANFIS modeling. It's called adaptive neural fuzzy inference system. Okay, this is a combination of what are called as the artificial neural systems and neural network systems and the fuzzy logic systems, which have a better predictability compared to ANN. We did also use ANN, but I'm not showing those studies. I'm only showing the latest studies that we have done, which is the ANFIS based modeling. So what you're seeing here is that the prediction given by the ANFIS modeling in terms of predicting the maximum temperature, as you see in the bottom pictures, bottom plots, compared to the actual, when we compare the predicted maximum temperature and the actual maximum temperature, the deviation is far well within the plus or minus 10%, showing a very good prediction of these models, which is the ANFIS model. So we found of the several models that we tried out, Gauss input and linear output membership function was the most suitable, whose results is what you're seeing over here. You're also seeing the results onto the left side of the table. This is the comparison of the actual versus the predicted surface temperature using the model that I just talked to you about. For different C rates, you are seeing the predictions are phenomenally good, and we were able to publish this in Journal of Energy Storage again, using the non-paraffinic organic phase change materials that I've used for cooling. Okay, it's already 9:05, a little over 9:05. I can go further, ask Professor Chinnapandian if I should stop here or go further. I think it would be better to stop here because there's more to talk on vanadium flow batteries. That would be another session, in fact. So I will stop here and take up some questions. Would that be fine, Professor?
Okay, Professor. Okay.
Okay. Because there's a lot that I should talk about on flow batteries and the studies that we have done. So I'm just stopping it here. Okay, so what I would like to say is that lithium-ion batteries are going to be really future. It's incredibly promising. We are going to see only more of it coming in. Only thing is we have got certain issues like the thermal management, which are to be sorted out to make it more safer and see much of its penetration in large scale into the market. That's what we see, and there are issues certainly. So we can work on innovative materials, advanced cooling technologies. Like, for example, there are a lot of gaps still in the immersion cooling techniques. We are also trying to work on certain material additions to the conducting fluids to bring the conductivity, means I'm talking about electrical conductivity, to the least possible, so that we will be able to use them for better cooling and so on. Smarter system integration, there's a lot of gap that we can work on. Novel battery designs, which chemists can also work on here to advance the penetration of the lithium-ion batteries. Good. Thank you very much. I should certainly thank my students. Satyanarayana, my former MTech student who worked with immersion cooling, is currently working with Stellantis, an automotive company in Chennai, as a senior engineer. My PhD scholar, Dr. Mutyam, worked on PCM-based cooling. He's a senior engineer working with Renault Nissan Technology and Business Center, India, Chennai. And currently, I'm working with high energy batteries, where Mr. J. Ramesh is working on, with me as a PhD scholar, part-time PhD scholar, working on vanadium flow batteries, redox flow batteries. So I certainly must thank them. It's their work under my guidance that I presented to you all. Thank you very much for your patient listening.
Thank you, sir. Thank you, sir.
Thank you very much.
Any questions from participants?
It's too late for questions, I think.
I'll ask one more question, sir, from my side.
Yes.
So you told that PCM-based cooling is requires a lot of volume, no?
Volume, correct.
What about futures? Any future for PCM-based cooling, sir?
Yes, certainly there is a future. And as I told you, to bring down the volume means that we'll have to improve the heat transfer rate. That would certainly require for lesser amount of PCMs, which would bring down the volume. If we have to use a lesser amount of PCM, then it means we have to improve their thermal conductivity properties. So that can be done by what are called as additives. Like I spoke about two additives, which is called as the expanded graphite, and the other one is called as the biochar. So there are a lot of different additives that are being studied in the literature. So by coming up with shape-stable composite PCMs, we will be able to reduce the quantity of PCMs required to remove enough amount of heat to keep the batteries within the desired temperature range of 15 to 40 degrees. That would certainly make the PCM-based cooling more attractive.
Yes.
And a lot of people are working on that.
Yes. Thank you, sir. Thank you.
Dr. Ruben, this is the earlier speaker, Irangovan here.
Wonderful, sir. Yeah.
Just a wild thought, okay? Because there's a lot of research scholar community in this call, and I thought I will put this idea forward for you to carry forward, okay?
Wonderful.
So
please go ahead.
There is a lot of heat that is being generated in the batteries. So that is an energy that is dissipating, right? Correct. So I'm thinking instead of using an external media, to cool this one, I'm thinking, say, can we take a refrigerant? Just an idea, okay? Refrigerant. Can that refrigerant acquire the heat, pressurize itself,
Okay.
go through a Joule-Thomson expansion valve,
Okay.
cool, and then
Okay.
make it a self-sustaining, what do you call it? Like a heat pump.
Yeah, heat pump, I think, see
Something like that. Maybe
yeah.
heat pump is
Yeah,
not the right word,
yeah,
but
yeah.
so since you got like mechanical people, and I'm not sure if there is any chemical, so I'm just thinking, because we want to make it self-sustaining, right? So
Yeah.
so
That's a
can
very
they
good
come
thing.
out with something, you can encapsulate the entire battery, and then on one side, there is a medium that picks up the heat, pressurizes itself, and then goes through an expansion valve, experiences a Joule-Thomson, like a refrigerator, So instead of external energy, the dissipation energy, can it be harnessed and then self-sustaining?
Certainly, people are trying out refrigerants in a very small way, but the problem is that the, uh, the enclosure where the heat is being liberated is going to be an evaporated section of the refrigeration system that we are talking about. So you need some other external power to drive this refrigerant through the cycle, thermodynamic cycle, to cool, to continuously cool.
Right.
Yes, certainly Joule-Thomson effect will help.
The idea, emanated from my experience in the, LNG sector. Okay. In the LNG sector, right? They liquefy the methane and then create the liquefied LNG. And then initially they'll start with a refrigeration compressor to start the refrigeration process. But after that, the same natural gas which goes through that, the main cryogenic cooler is self-sustaining. They switch off the refrigeration compressor. No need. It is self-sustaining. There is an evaporation taking place, taking up the heat, so it's chilling the the incoming fluid. So it is self-sustaining, and then the process is highly energy efficient. So I'm just thinking, it is called the main cryogenic cooler in an LNG plant. So if we can adapt the same concept, I think there might be a breakthrough. I'm just using my
we can certainly
marketing
think about
and sales.
it. We can certainly think about it in this direction. Only thing that kind of the thought that's moving in is like the compressor that we talk about to compress the refrigerant is an energy intensive unit, as you must certainly be aware of. So that's where whether the benefits that we get out by using the refrigerant will outweigh the electrical energy required to run the compressor. But certainly it's an interesting idea.
I'm not suggesting to put a compressor. What I'm saying, there may be a fluid. There may be a fluid. When it is heated up, it pressurizes. For example, right? If I have a limited volume, and if I put one drop of LPG, right? If I maintain at room temperature, it may remain at say 1 bar. Now, if the temperature goes up, right, that same mass of LPG that I put inside is going to increase to 5 bar, 6 bar. Then the 5 bar, 6 bar, I put it through a Joule-Thomson expansion valve. When it goes to Joule-Thomson, the other side it's chilling. The temperature will be cold. So I'm just thinking, a closed circuit. No initial startup, maybe external energy may be required. Then after that, it's self-sustaining.
Yeah, certainly an interesting idea. We will have to pursue this and then see how it works. Certainly an interesting idea. Thank you.
Thank you so much, sir. Thank you so much.
Sir, good evening, sir.
Good evening, sir.
Sir, whether PCM is used as cooling media for that commercially available e-vehicles right now in India, sir?
No, sir, not yet. Not yet. Certainly not yet. Any type of immersion. See, basically, this is the module is going to be immersed in the PCM. So this immersion type of cooling is something that is not still available in the commercial scale vehicles yet, but they are certainly moving towards that. Like I told you about the 3M fluid Novec, which is very expensive as of now, is something that's really looking promising. So they might come up with it, but as of now, as far as my knowledge goes, I don't see any commercial vehicle operating with this immersion type of cooling at all, with the PCM or the liquids that we were talking about.
Okay, sir. One more clarification, sir. What kind of PCM are in research for this cooling, sir? E-vehicle battery cooling.
Okay, sir. There are n number of things. For example, we are working currently on what is called as an eutectic-based PCM, organic, inorganic, and so on. There are so many, and a lot of people are working on new PCMs. So you can see so many, hundreds of them, in fact. But only problem is that the performance is a question. So we have synthesized certain PCMs here with ourselves, new PCMs, and then we have tried it out using biochar as an additive, and then expanded graphite as additive. We used organic PCMs first, and then also non-organic PCMs later, and now we are working on eutectic PCMs.
Okay, thank you, sir.
Thank you very much. Thank you. I appreciate the interest of Mr. Ilangovan, having been here after his lecture. Thank you very much, sir. It's really motivating.
My pleasure. I've been listening to all the speeches. The last today is the 5th day, right? All day.
Wonderful.
And I'm also hungry for knowledge.
Wonderful. I could see that visibly.
Professor, questions from chat box. How to protect batteries in immersion cooling?
Yeah, that's a very good question. So basically, I think the question technically is like, see, we have got an electrical system over there, and we are sending some fluid inside. Will the fluid not conduct and then lead to short circuiting? I would read it as that way. So that is why I said the fluids that we have used, basically terminal oil and the mineral oil, are dielectric in nature. Low-cost dielectric fluids is what we have used, which are not conductors of electricity. Now we are moving. The only problem with such dielectric fluids is that the thermal conductivity will not be very appreciable. So now we are moving towards taking up with the electrically conducting fluid, but then we somehow subdue it by adding some additives to either the surface of the batteries or additives to the liquid, so that we can see to that there is no electrical conductivity prevailing there, and still have a very good thermal conductivity of the fluid, so that we can remove heat. So that's what we are looking at. So the answer straightforward to the question is that currently the liquids that we are using is dielectric.
Another question, sir, is there any potential to increase charging cycle? Is there any potential to increase charging cycle?
Yes. If you are able to keep the battery within the desired limit of 15 to 40 degrees Celsius, it already means that the battery is not deteriorating during those cycles that are operated under these temperature ranges. That indirectly means your lifespan of the battery is going to be more. Means your discharging cycles are going to be better. Means the first discharge cycle, you will have a better performance. Probably it may not be the case in the 500th cycle or 1000th cycle. But if you maintain the temperature range within what is desirable, then the performance would not degrade much even after 1000 cycles or 1500 cycles, is what I am trying to say.
Yes, sir. Sir, another question, sir. How can I convert charging rate to current flow? How can I convert charging rate to current flow? Questions from Dr. Tarael.
Okay, this is basically C rate, I think you are referring to. It's the ratio of ampere hours to hour, right? If, let's say, I have a battery with 4.6 ampere hour battery, and if I am able to take 4.6 amperes from this, draw a current of 4.6 amperes, it will last for 1 hour. Then it means that I am operating at 1 C rate. So if you fix the C rating, you are fixing the current that you can draw. You get me? So if you are going to have a 2C rating, then you will have it only for you will have the discharge cycle for only half an hour. Similarly, if you increase it to 3C rating, then further down and so on. So your C rating will fix the maximum current that you will be able to withdraw from the battery. That is what it indirectly means when we say C rating.
Okay, sir. So any other questions from participants? Otherwise, I will have a screenshot. Please unmute your camera. Now I call upon Mr. Kaliraj to give formal vote of thanks to your
okay, sir.
speaker. Okay. Kaliraj?
Okay, sir. I will. Once again, I will give very sincere and thank you, sir, for your enlightened and lecture on battery storage systems related to oil lithium battery used and comparison between the various battery cooling systems, then impression cooling system, then maximum surface temperature related to various types of cooling systems. It's all very enlightening topics. Then thank you for coordinator and co-coordinator for arranging this kind of lecture related to adult FTP. Finally, thank you for all the participants who listened in the late evening. Finally, one and all, thank you, one and all.
Thank you. Thank you, sir. Thank you, sir. Ruben, sir. And,
Thank you very
sir.
much for
Thank
the
you, sir.
opportunity, sir. Thank you
Thank
very
you,
much.
sir. Thank
Thank you. Thank you.
Thank you, sir.
Dear participants, for tomorrow's session, last session, please come earlier. Session starts from 2 to 3 p.m. First session tomorrow, and then 3:30 to 5 p.m. second session by Dr. K. Purushothaman, and 2 to 3 p.m. by myself, and the topic of cascade latent energy storage, and then 3:30 to 5 p.m. the Dr. K. Purushothaman is going to talk about the community of bioenergy storage, opportunity and benefits, and then we have last session, Dr. Shafi T. Agriculture, energy storage and conservation solution for farmers and ranchers. And then after that, 7:30 to 8 p.m. We are going to conduct online test and feedback. And then finally, our validity function from 8 to 8:30 p.m. So kindly come earlier, and then we will 150. We will start by 150, please. Okay. So thank you all. Thank you all once again.